Okay, after we've gone through some of the theory on CPS, I want to give you a few examples in Scala. This is just out of the continuation passing style notebook and the week's readings. And we're just going to go over factorial and the Fibonacci sequence, our favorite examples. All right, so here we have factorial. What does it do? It takes in an int, returns an int. If n is less than or equal to 0, we return 1. Otherwise, we call factorial n minus 1 and multiply it by n. In these sort of situations where we might have a single line like this, it's usually handy to break it down into multiple lines. That way we can really see what the order of operations is, right? Because if I was not paying much attention, I might think this is already a tail recursive call, right? Because the last thing I do is seemingly call factorial on n minus 1. But really, this is val v that's going to be equal to factorial of n minus 1, and then we return n times v. So that's why we don't actually have tail recursion here. All right, so how do we change this to a tail recursion? Well, first, let's make sure that Scala recognizes that this function is tail recursive. Right, we import Scala annotation.tailrec, and then in front of the tail recursive function, we're going to just put this annotation at tailrec. And so we're going to make this new form, this CPS form of factorial, which we're going to call factorial sub k. K is for continuation, obviously in the German. And what do we have on the inside? We have, it takes an n, which is an integer, as we are used to, and then it takes in a continuation k, which should take in whatever the return value is of the original function. So it should take in an int, and it should return, well, what should it return? In this case, we could say it returns an int, but we actually could do it as a completely generic t. And we do that by putting this little t in square brackets right after the name of the function. And what this is doing is it's making it say that factorial sub k is a generic function that, depending on what this t is, we'll get different versions of it. And t is completely replaceable. So the idea is that I don't necessarily know what the function that's going to call factorial k wants to do to it, right? Maybe it turns that integer into a string, maybe it computes something with it and I get a double out. There's a lot of different possibilities of things that I might want to do with the factorial of, say, 6. And I want to leave that those possibilities open. So I don't want to necessarily say that it has to take in the answer to factorial and then return another int. So yeah, what do we do here? Well, we have our base case, right? If n is less than or equal to 0, I want to return 1, but remember, I don't ever want to just return the basic value out. I always want to wrap it in my continuation, right? The k is the function that whoever called factorial of k handed to me and said, hey, when you're done with factorial, run k on whatever you got, whatever was returned to you, right? Whatever you came up with. And so if n is less than 0, then I know that I want to return 1. So I want to run my parents' continuation on it, right? I want to run k on 1. Otherwise, what do we do? Well, we're going to want to basically wrap up this part into a new continuation, right? The idea is that this is the last function call I have, so I want to make this tail recursive. And I do that by passing in this computation as a continuation. So the idea is here, what is a function representation of this, right? N times v. Well, it takes in v, right? That's my parameter, and it returns an integer. And what is it going to be? Well, it's n times v, right? And of course, because that's the last thing I want to do here for my factorial k, I want to make sure that I call my parents' continuation on it. All right, and now I can call factorial sub k after I made this definition of the continuation with n and k1. Right, I might not want to have to make this full function definition and give it a name, in which case I can always do it with a generic or with an anonymous function, right? That'll take v and apply v times n. right? So this is equivalent. I want to make sure that, right, type mismatch, it says it found a t and it requires an int. K should take in an int, and yeah, this all looks fine. Maybe I want that as a t. There we go. Right, K1 was returning an int, and whatever I pass into factorial K here, I said should be returning a t. Mostly because whatever K does, right, I said K is going to return a t. So if K1 takes in an int, multiplies that int by a number, and then applies K to it, well, K is going to take that int, or V times n, that int, and return a t. So I want to make sure that K1 also returns a t, even though I'm not using it, right? So yeah, this is our continuation passing style version of factorial, and it should be fully tail recursive. And we can even run it on, let's see, factorial sub k on, let's say, 10. And then, well, what continuation do I want to put here? Typically, you want to do the generic identity one, which just takes v and returns v. Right, so the idea is my final continuation, I don't actually do anything. I just return a number. And while the Scala kernel kicks up, ooh, did you see the error that I have here? Right, what's the issue? I need this to be n-1, otherwise it was going forever. Right, I was never approaching my base case. Okay, let's try that again. Oh, good. Much faster this time. All right, always double check that you're actually inputting the right values into your function. Cool, so that's factorial, right? We can run this on multiple things. We can try 6. I can also change what my final function is, right? I could do, say, something like toString, and that returns not the number, but an actual string, right, in quotes 72. I could also say v, and then I'm going to say print line v. All right, this returns a unit, but what it does is it prints 720. Maybe I wanted to do something else with 720, like say multiply it by or divide it by 1,000, right? And I get 0 because I'm doing it as integers, so let's do 1,000.0. I get 0.72. All right, so this final continuation is sort of the extra bit of computation you can always toss on top of your factorial. And if you don't need anything, then yeah, just do the identity transformation, which sends v to v, right? So whatever factorial k eventually ends up with, it just returns that. Yeah, let's take a look at Fibonacci, right? A little more complex. Fibonacci, we have if n is less than 2, then we return 1. Otherwise, we return the sum of n-1 and n-2. Again, I'm going to rewrite this into multiple lines just to make the order of operations clear. So val v1 is Fibonacci on n-1. Val v2 is going to be Fibonacci on n-2. And then I'm going to return v1 plus v2. So hopefully this makes it a little clearer when we go through the CPS transform. Again, I'm going to turn this into the generic type instead of actually returning ints. So what do I actually change here? This little annotation that says that Fibonacci k is has a generic type t, and then the continuation passing, or the continuation is going to take in an int, whatever the original function returned, and now it's going to return a t instead. And then my whole function is going to return a t, because always the last thing I do is call k on whatever I was going to pass back, right? So whatever I was going to pass back was an int, k transforms that into a t, and then I return that t directly. So in our base case, what do? We have if n is less than 2, we just call k on 1, right? The thing that we were originally going to return, but now we're going to make sure to wrap it in all of that extra computation that my parent wanted me to do. Else, what are we going to do? Well, we want to be able to break this up, right? So what do I have? The first call I have is this call to Fibonacci n minus 1. Then I'm going to call Fibonacci of n minus 2. And then I'm going to add up what I get from both of them and return that. So CPS is a little weird, right? Because we're sort of we want to make sure that the Fibonacci call, or the call to Fibonacci of n minus 1 is the last function call that we have in our entire CPS form, which means that we need to write up these two statements as continuations. So what do we want to do after we call Fibonacci of n minus 1? Well, I want to do both of these things. Right, so I'm going to call this continuation K1. It's going to take an integer V, and it's going to return a type T. And what's it going to do? Well, it's going to call Fibonacci of n minus 2. Actually, I'm going to change this to V1 to make sure that this matches up with our original definition here. Right, so the idea is K1 is going to be, I call Fibonacci of n minus 1, I get V1, and I do something to it. Well, what do I do to it? I do these two lines of code. And I want to wrap that up in this function named K1. So what does K1 do? It takes in V1 and it's going to return a T. And, well, it's going to call Fibonacci of n minus 2 with whatever is after that function as another continuation. So I'm going to call this line of K2. So K2, what does that do? It takes in V2 and it takes, which is an int, returns a T, and it's going to call K on what? V1 plus V2, right? So it's just this line of code wrapped in the original parent K, right? So K comes from up here. And so K2 basically just takes in, is this line. Right, so then we call Fibonacci of K on n minus 2 with K2 as the continuation. So that's these two lines all wrapped up. And that's all inside of K1. Right, so that's what K1 does. And then we call Fibonacci of K on n minus 1 with K1. Right, so that's the idea here is that it's basically this line with all of this computation wrapped up and fed to it as K1. And we see that this still works, both of them work, right? So I have Fibonacci of 12 and Fibonacci K of 12 with the identity continuation there, and they both give me 233. One thing I want to do real quick is just write this up in a single line just so you can kind of see what that looks like too. Right, so the idea is that I want to make sure that this is tail recursive, but I don't want to write up all of these continuations with names. So I'm going to do this instead. I'm going to try Fibonacci sub k of, well, I know the first thing I want to do is n minus 2. And then I'm going to get this this value called f1. Sorry. Right, I want to do the final call here is going to be this first one, right? N minus 1. Whatever I get back from my original sort of form of Fibonacci n minus 1, I'm going to call that V1. And what do I want to do with V1? Well, I want to call Fibonacci k on n minus 2, which will return some value called V2 that I want to do something with. What do I want to do? Well, I want to return V1 plus V2. But not just that, right? I want to actually wrap this up in K as well. And let's see, do I have all the parentheses in the right place? Yeah, that seems to work. And that still works just fine. So this is everything sort of condensed onto one line. And the goal here is to sort of notice, right, how did I do this? I take the first function call to the n minus 1. And then whatever the variable name I gave here is what I give to my stand-in for my anonymous function here, right, as my parameter. And then I wrap up all of this equation, or all of this computation with everything inside of my brackets here, which is what I call Fibonacci of n minus 2. I get this v2 back. And then I do whatever else is left over, which is just going to be adding v1 to v2 and applying k to it. And since all of this stuff is defined, right, so this whole thing is defined inside of the definition of v1, I get that the scoping works out just fine for this. So yeah, that's cool. What happens when we run, say, Fibonacci of k on a larger number, right? Looks like 18 is pretty bad. What about 17? Oh, I still get the stack overflow error. What about 16? And let's see, 15. Oh, that actually worked, right? So looks like I can do Fibonacci of k up to 15 before I get a stack overflow error. And what's going on here? Well, right, I was able to do the normal Fibonacci numbers, say even up to 20 or bigger. And that's fine. And that's just because, right, the stack height of the Fibonacci sequence is at most 20 for the original style, right? The problem was that we end up going up and down the recursion tree because we're doing this double sum, right? But for the continuation passing style structure, what we've done is we've taken that entire recursion tree and flattened it all out into one long recursion chain. And Scala doesn't see this naively as tail recursive, so it just keeps on adding all of these function calls to the stack. And so we can't get above really 16 or 15, right? 15 is the limit. 16, right, there's about 2 to the 16 calls, so that's where we're getting the stack overflow error, is we've basically put on 2 to the 16 function calls onto our stack, and that's gone overboard. So we could do things like, you know, add the little tail rec with the hope that Scala will be able to optimize this effectively. But as you see here, we get this error that says we could not optimize this method. It contains a recursive call, not an tail position, which isn't true. All right, we built this up so that it is a tail recursive call. This is just like the version that I made above, right, where Fibonacci k on n minus 1 then takes Fibonacci of k on n minus 2 as its continuation, and then that takes v2 of k of v1 plus v2. So this is tail recursive, but Scala's just not smart enough to be able to pick that out. And other languages actually handle this better than Scala does. Scala just basically throws this error at us saying that, oh, I can't turn that into tail recursive, even though it can be. So like Python does this well, and we're gonna see in the next video, essentially on trampolines and thunks, how can we actually take this and then manually handle the stack ourselves, right? So we don't necessarily need to let Scala figure out how to do tail recursion under the hood, because we know what the optimization we really want to do with tail recursion is, right? We want to be able to say, once you're done with the subcall, right, erase yourself from the stack. Don't worry about waiting around for the return value. Just dump yourself off the stack and, you know, change your parent or change your child's return call to your parent's return call. And we'll see how to basically handle that on our own with trampolines in the next video.